everyone, this is Srikanth as Assistant Professor of EEE Department. In this session, I am going to cover the common emitter configuration of transistor. The name itself says there is a emitter is common between the base and collector. Here, the common emitter configuration, base is the input terminal and collector is the output terminal, and emitter is the common terminal for both input and output. Here in this configuration, emitter we are making it as common and base is the input and collector is the output terminals. Here the base terminal and common emitter terminal are known as input terminals. Here for the input, the two terminals are base terminal and emitter terminals. And whereas collector and emitter terminals will work as the output terminals. In common emitter configuration, the emitter terminal is grounded. So the common emitter configuration is also known as grounded emitter configuration. Common emitter configuration is also known as grounded emitter configuration. Sometimes common emitter configuration is also referred as CE configuration and common emitter amplifier or CE amplifier. CE is nothing but it is a shortcut form of common emitter. So we can call it as CE configuration or CE amplifier. And the common emitter configuration is the most widely used transistor configuration. This is one of the most widely used transistor configuration. That is, generally we are going to take the emitter as the common terminal. And this is the basic circuit diagram of common emitter amplifier. In this, always we need to have emitter junction is forward bias and collector junction should be a reverse bias. So for that, here we are making the emitter as common. This is the common terminal or grounded terminal. We are making this emitter as the common terminal, and for base we are going to give the input. If let us consider it is of NPN transistor. It is of NPN transistor. When it is NPN transistor, base to emitter junction should be forward bias. In order to make the transistor in active region, in order to keep the transistor in the active region. So we are going to make the base to emitter junction as forward bias. To make the base to emitter junction forward bias, P layer is connected to the positive of VBE and N layer is connected to the negative of VBE. When the P layer is connected to positive of VBE, then the holes in the P layer and this positive voltage will repel each other. Holes in the P layer and positive voltage will repel each other. So because of the repulsion, the holes will move towards the junction. So the depletion layer will get reduced. When the depletion layer is reduced, at certain voltage, the conduction will take place from base to emitter junction. and here the negative voltage is given, and here in the n-type layer also the electrons will move towards the depletion, move towards the junction, so that a narrow depletion region we are going to get between the base to emitter junction. And here collector to emitter junction, here collector to emitter junction should be reverse bias. So positive voltage is connected to n-type layer. So the electrons in the n-type layer are going to attract towards the positive voltage. Hence the depletion layer will increase. So always emitter base junction depletion layer is narrow, and collector to emitter junction will be broad. The depletion layer of collector to emitter junction will be broad. And here is the current flow, that is, this is the collector current IC, this is the base current IB, this is the emitter current IE. So IE is equals to IB plus IC according to Kirchhoff's current law. What is Kirchhoff's current law? Whenever a current enters any junction, that should leave from the junction, or sum of currents entering the junction is equals to sum of currents leaving from the junction. Here sum of currents entering the junction is IC plus IC and IB. So IC plus IB is equals to IE. Here IC plus IB is equals to IE. Here the common emitter amplifiers are used when the large current gain is needed and the input signal applied between the base and emitter terminals, while the output signal is taken between the collector and emitter terminals. Thus, the emitter terminal of transistor is common for both input and output, and hence it is named as common emitter configuration. Here, the emitter terminal of transistor is made common. That is the reason why this configuration is named as common emitter configuration. Here the supply voltage between the base and emitter is denoted with VBE, while the supply voltage between collector and emitter is denoted with VCE. Here whatever the input voltage which we are giving to the base and emitter junction, that voltage is named as base to emitter voltage, VBE, the shortcut form of base and emitter. And while the supply voltage between the collector and emitter is denoted with VCE, where C denotes the collector. And in the common emitter configuration, the collector current is denoted with IC, and emitter current is denoted with IE, and base current is denoted with IB. So here the common emitter has a medium input and output impedance levels, which is going to have the medium input and output impedances. So the current gain and voltage gain of the common emitter amplifier is medium. However, the power gain is high. Even though the impedance and current gain are medium, but the power gain is very high with the common emitter configuration. And to fully describe the behavior of the transistor with the common emitter configuration, we need two set of characteristics. One is input characteristics and output characteristics. Now first let us go with the input characteristics, and here the input parameters are the base to emitter voltage and base current. The relationship between the input current and input voltage is nothing but the characteristics, the input characteristics. And here first we need to draw a vertical and horizontal line. The vertical line represents y-axis and horizontal line represents the x-axis. Here IB is taken along the y-axis and the VBE is taken along the x-axis. The voltage value is taken on the x-axis and current value is taken on the y-axis. Here, to determine the input characteristics, first in order to get the transistor into active mode, first we need to keep the base to emitter junction as forward bias and collector to emitter junction as a reverse bias. So in order to keep the active region, we need to keep the VBE in the forward direction and VCE in the reverse bias condition. So here the output voltage we need to keep at some constant value. The output voltage we need to keep at some constant value at 0 volts or 1 volts, 2 volts, 3 volts. Like that we can change the VCE value, and after keeping the VCE value at constant either at 0 volts or 1 volts, the input voltage is increased. VBE is increased from 0 volts to different voltage levels. When we are changing the input voltage, for each step we need to note down the base current corresponding to the input voltage. Corresponding base current we need to be recorded. Once it is recorded, we need to draw the characteristics. So here this is our base to emitter voltage and this is our base current. This is our base current. When let us consider the VCE value as 0. When we have considered the VCE value as 0, the base to emitter junction will be forward bias after the cut-in value. After the cut-in value, the conduction will take place. So the base to emitter junction, which is going to have a small current once it reaches the cut-in value. Once it reaches the cut-in value, immediately within a small change in voltage, the current will increase to maximum. Current will increase to maximum. So this is at 0 volts. After that, we have to keep the VCE value at some other value other than 0. Here it is considered that at 10 volts. At 10 volts, when we keep VCE 10 volts, and again we have to take the values for the input voltage change and corresponding input current change. So the characteristics will be a small change will be there because of the collector to emitter voltage, because of when there is a increase in the collector to emitter voltage, when there is increase in the collector to emitter voltage, there will be a difference in the electron hole pairs creation and electrons movement. So because of that, some change in the characteristics we are going to observe. And in the same way, when we go on increase the VCE value, and there will be some change in the characteristics, the input characteristics for the common emitter configuration. Like this, by changing the different collector voltages, we are going to draw the characteristic for the input base voltage and base current. Now we will go with the output characteristics. Before going to the output characteristics, a curve is drawn between input current and the input voltage VBE at constant output voltage VCE is equals to 0, and this is the next point which is increased with where VCE is kept at 10 volts, and while increasing the VC output voltage, the input voltage is kept constant at 0 volts. After we kept output voltage constant at 10 volts, the input voltage is increased from 0 volts to different voltage levels. And in the same way, for each voltage level of input voltage, the corresponding IB current is recorded. And this process is repeated for higher values of fixed output voltages VCE. Like we have taken in the graph, we have seen VCE at 0, VCE at 10, VCE at 20. Like that we can change the different values of VCE and we can check the input characteristics. And here the input characteristics of common emitter configuration is similar to the normal PN junction diode characteristics. Here the cut-in voltage of silicon transistor is 0.7 volts and the germanium transistor is 0.3 volts. In our case it is a silicon transistor. So we are having the cut-in voltage of 0.7 volts. That's why after 0.7 volts only the current is increasing. You can see clearly in the characteristics. Here this is the 0.7 point. All the values are highly increasing. To this, a small increase in the current, but after this point a huge increment in the current value. Within a short change in voltage, the current value is increased with a large value. In the common emitter configuration, the input current is very small as compared with the input current. IB value is very small as compared to the input current IE in the common base configuration. Whereas input current in CE configuration is measured in microamperes, whereas the input current in CB configuration is measured in milliamperes. Here, when we compare the common emitter and common base configuration, the input current value is very less in the common emitter configuration as compared with the common base configuration. Whereas when we go with common emitter configuration, the input current is in microamperes, whereas in common base configuration, it is in milliamperes. In common emitter configuration, the input current is produced in the base region, which is lightly doped and has small width. Why we are having the less current in the input current is because the base in the transistor is lightly doped, which has small width. So the input current is the base current, which is of very less value. So the base region produces only a small input current, that is IB. On the other hand, common base configuration, the input current is IE, which is produced in the emitter region. In the common base configuration, the input current IE is produced in the emitter region, which is heavily doped and has large width. So the emitter region produces a large input current. Therefore, the input current produces in the common emitter configuration is small as compared with the common base configuration. because of in the common base, emitter current is the input current. So emitter is heavily doped and which has large weight, so the current will be more. Here, due to the forward bias, the emitter base junction acts as a forward bias diode, and due to the reverse bias, the collector base junction acts as a reverse bias diode. Therefore, the width of depletion region at the emitter base junction is very small, whereas width of depletion region at collector base junction is very large. If the output voltage applied to the collector base junction is further increased, the depletion region will further increases. So the base region is lightly doped as compared to the collector region. So when the base region is lightly doped, because of that, the depletion region penetrates into the base region and less into the collector region. Now, as a result, the width of base region decreases, which in turn reduces the input current which is produced in the base region. So when we are changing the VCE value, the curve is shifting towards the right side. This is because of high fixed values of output voltage. The cut-in voltage is increased above the 0.7. When we are changing the VCE value, because of the VCE value, the cut-in voltage for the input side is going to vary. Therefore, to overcome this cut-in voltage, more input voltage is needed than the previous case. In order to overcome the cut-in voltage, more input voltage which is required than the previous case. Now we'll go with the output characteristics. The output characteristics is the relationship between the collector current and collector to emitter voltage, or that is output current versus output voltage. And here we need to draw the vertical line and horizontal line. The output current or collector current is taken along the y-axis and the output voltage is taken along the x-axis. In order to determine the output characteristics, first we need to keep the base current at 0 microamperes, because always base current will be in microamperes. So, and the output voltage is increased from 0 volts to different voltage levels, and we need to record the VCE and IC values. And here is the VCE voltage, VCE versus IC, and here is the when the IB value is at 0 microamperes. When IB value is at 0 microamperes, we are going to get a small amount of leakage current, that is IC, as the output. When we increase the base current, because we know that transistor is a current control device. Which current control? Base current control. Once the base current is increased from 0 to 20 microamperes, when the base current is increased, automatically the collector current increases. Here the collector current is increased, and like that when we go on changing the base currents from 20 amperes to 40 amperes, 60 amperes, 80 amperes, 100 amperes and 120 microamperes, here the collector current also increases. The collector current is also increases, and below the collector current 0 or only the leakage current, that region is called the cutoff region. That region is called the cutoff region. And where the current exists in the transistor, that region is called the active region. Before switching on, whatever the region which until it takes the actual value of current, actual value of collector current. This particular region is called the saturation region. Here a curve is drawn between the output current and output voltage at constant input current. And when the base current is at 0 degrees, transistor operates in the cutoff region, and in this region both junctions are reverse bias. In this region both junctions are reverse bias. Next, the input current is increased from 0 microamperes to 20 microamperes by adjusting the input voltage VBE, and the input current is kept constant at 20 microamperes. Like this, by increasing the current value, input base value, and we need to change the output voltage, and we need to change the output voltage, and we need to note down the output current. So when the current in the collector is available with some values of base current, either it may be 20 microamperes, 40 microamperes, 60 microamperes, this particular region is known as active region of the transistor. In this region, emitter base junction is forward biased and the collector base junction is reverse biased, and these steps are repeated for higher fixed values of input voltage IB, that is 40 microamperes, 60 microamperes, 80 microamperes, and so on. Here, when the output voltage is reduced to a small value 0.2 volts, the collector base junction becomes forward bias. This is because the output voltage has less effect on the collector base junction than the input voltage. Here, when VCE value is reduced to a small value, collector base junction will be forward bias. So, because the output voltage has less effect on the collector base junction than the input voltage. As we know that the emitter base junction is already forward bias, therefore when both junctions are forward bias, the transistor operates in the saturation region, and in this region a small increase in output voltage will rapidly increases the output current. Now we'll go with the transistor parameters. The first one is dynamic input resistance. Here the dynamic input resistance is defined as the ratio of change in input voltage or base voltage to the corresponding change in input current or base current, with the output voltage or collector voltage kept constant. That is, Ri is equals to delta VBA by delta IB, where VCE value is at constant value. That means if we go on changing the VCE value, we should not take the change in the base to emitter voltage for different VCE values. We have to take only for one particular value of VCE, we have to calculate delta VBE and delta IB. And in this configuration, the input resistance is very low. And now we'll go with the dynamic output resistance, where dynamic output resistance is defined as the ratio of change in output voltage or the collector voltage to the corresponding change in output current or collector current, with the input current or base current kept constant. Here we are keeping IB value as constant, where R naught is equals to delta VCE by delta IC. In CE configuration, output resistance is high. And current gain, the current gain of CE configuration is defined as the ratio of output current or collector current to the input current or base current. Current gain is nothing but output current by input current. Here the output current is collector current and the input current is the base current. The current gain of the transistor is very high under the CE configuration because the base current value is very less in microamperes we can see. Therefore, the transistor in CE configuration is used for amplifying the current. Here, the current value is more, that is, current gain is more. So, in order to use this transistor in a perfect way, we have to use this transistor in high current wherever we require high amplifying current applications. Here transistor orientation, for NPN and PNP transistor both can be used for common emitter configuration. For an NPN transistor, the emitter is connected to ground, while PNP transistor, the emitter is connected to the supply voltage. The input and output characteristics, the input voltage is applied to the base and emitter terminals. The output is taken between collector and emitter terminals. And here the amplification, the common emitter configuration provides the voltage amplification. The voltage gain in common emitter configuration is relatively high compared to common base and common collector configurations. And here the inverting amplifier, if the output signal is 180 degrees out of phase with the input signal, making it an inverting amplifier. In this, output signal is exactly 180 degrees out of phase with the input signal, so which is making as inverting amplifier. And high input impedance, moderate output impedance. In this common emitter configuration, it has high input impedance because input current is very less, so the impedance will be more, and the output impedance is moderate, making it suitable for driving loads with moderate impedance. And the next one is biasing. Proper biasing is crucial to ensure the transistor operates in the active region, and biasing arrangements includes using resistors and a DC power supply to set the operating point. Here the proper biasing is crucial to ensure transistor operates in the active region. And biasing arrangements includes using resistors and a DC power supply to set the operating point. Now let us go with what is operating point. The operating point, also known as the Q point, is the DC bias point where the transistor operates for linear amplification. And the Q point is set by choosing appropriate biasing resistors. Here, this is the point where the transistor operates in the linear amplification. That point is called the operating point or Q point. The applications are the common emitter configuration is used in applications requiring the voltage amplification such as audio amplifier, and frequency response in common emitter configuration has a bandwidth that may be limited by parasitic capacitances and other factors. And the next one is AC and DC analysis. And AC analysis focuses on the small signal behavior of signal amplification. And here the DC analysis considers the biasing and operating point of the transistor. And these are some of the applications of common emitter configuration. Here, the first one is the audio amplifier, where here we are going to get high voltage gain. With this, high audio amplifiers are going to use this common emitter configuration of a transistor, and microphone preamplifier and class A power amplifiers and radio frequency amplifiers. Here, the signal modulation, the common emitter configuration can be used in amplitude modulation circuits where it helps modulate the amplitude of carrier signal with an input signal. And the next one is tuned amplifier. These are nothing but where we can use this tuned amplifier in radio frequency applications where specific frequencies are needed to be amplified. And oscillators, in the oscillator circuits, some CE configuration is used to generate the periodic waveform such as unstable multi-vibrator circuits. And signal inversion, here the voltage whatever we are giving, that is becoming 180 degrees out of phase. So that signal inversion is happening in the natural way. So the phase shift of the signal is acceptable. In that particular applications, we are going to use this common emitter amplifier. And voltage regulator, the common emitter configuration is sometimes used in voltage regulator circuits and in order to maintain a stable output voltage. Here the temperature and light sensors. The transistor based temperature and light sensors often use common emitter configurations. And also amplitude modulation, because we are having the voltage gain is very high in the common emitter configuration. So wherever we require amplitude modulation or demodulation, we can use the common emitter configuration. And biomedical applications. Here the common emitter configurations can be found in biomedical instrumentation such as amplification in the bioelectric signals from sensors. So in this session we have discussed the working principle of common emitter configuration of a bipolar junction transistor and the input output characteristics and what are the advantages and applications of common emitter configuration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.